This flume should be familiar to most inspectors. It's the Parshall flume, one of the most common flow measuring devices at publicly owned treatment works. Parshall flumes measure open channel flow using the critical depth principle.
Flumes can be installed in several places. This one's located at the headworks. You can also find the flume
just before the outfall of the plant, anywhere you have open channel flow measuring requirements. The Parshall flumes are very accurate and have low head loss. They can handle the high suspended solids commonly found in the raw waste streams without losing accuracy, and they can measure a wide range of flows. Permits issued under the National Pollutant Discharge Elimination System, or NPDES, typically require that the permittee accurately determine the quantity of wastewater being discharged from the plant. Accuracy is important because these flows are used for both the calculation of acceptable permit limits and for compliance monitoring and reporting of pollutant loadings.
So the plant needs an accurate and reliable flume and a good inspector who can spot problems and potential problems. Although each site will be different, there are 3 basic steps to an inspection of any flow measurement system.
These are: assess the flume, the primary device, assess the head measurement equipment, the secondary device, and verify the accuracy of the system as a whole. The Parshall flume has 3 sections: the convergence section, the throat section, and the divergence section. The flow comes into the convergence section and passes through the throat section where it is contracted. Throat widths of Parshall flumes, by the way, vary from 1 inch to 50 feet, depending on the expected range of flows at the wastewater treatment plant. After the flow passes through the throat, it enters the divergence section, which allows the water to flow freely away from the flume. Some flumes don't have this divergence section.
The principle for flow measurement in a Parshall flume is that channel restriction here at the throat produces a calibrated change in the liquid level and flow velocity as the flow rate varies.
There are several equations, depending upon the site of the flume, for measuring the flow in a flume. The basic formula relates the flow Q to the liquid head, where Q is the flow in cubic feet per second. B is the throat width in feet, and H is the liquid head in feet measured at a specific point in the convergence section. To make it easier, families of rating curves exist which correspond to different hydraulic conditions for a certain size flume. If the flume is prefabricated, like this fiberglass flume, these curves are available from the manufacturer. But if the flume is constructed on site, like the concrete flume you see here, curves need to be developed from the collection of site-specific data.
Most errors in flow measurement don't have a thing to do with tables, equations, or even calculations. The most common errors are improper location, construction, installation, and sizing of the flume. That's why a thorough inspection of the overall system is so important.
First, make sure the site meets the requirements stated in the NPDES permit. The permit usually states where the flume must be located in the process train of the plant. Check to see that the flume has been placed in an area free of turbulence. Next, check the integrity of the construction materials. Are they still in good condition? The flume we're inspecting is fiberglass, but some Parshall flumes are metal, some plastic, and some are made of concrete. It doesn't really matter what's used to build it, as long as the materials are corrosion resistant and smooth finished to maintain a solid, watertight foundation that maintains measurement accuracy. The flume should also be symmetrical. Make sure the side walls are smooth and vertical. You can check this with a carpenter's level. Check to see if the floor in the convergence section is level by checking the level at the surface and taking several measurements of the side walls. If the floor is not level, there won't be an accurate reading of the liquid head. And these errors will be significantly compounded the higher the flows through the flume. This flume was prefabricated, so we can assume the dimensions are relatively precise. Dimensions for flumes that are built in place, however, must be measured carefully against design specifications. A flume that is not constructed correctly will need extensive experimental testing to characterize the proper relationships between the level readings and the actual flow. The upstream and downstream channels of the flume also must be checked. The upstream channel must be straight, horizontal, and of a uniform cross-section for a distance of at least 10 times the flume throat width. The channel should be at least as wide as the mouth of the convergence section, and the convergence section of the flume should be merged flush into the channel walls for a smooth, rounded transition to avoid turbulence in the flow. Now let's look at the downstream channel. It's important that the downstream water levels are low enough to maintain free discharge conditions in the divergence section of the flume. There should never be any type of obstruction, constriction, or channel turns immediately downstream that could cause the flow to back up into the flume.
Remember, the goal is to have free flow through the flume at all times.
Sizing of the flume is very important. First, check historical records to see that the variations in flow are within the range for which the flume is accurate. Several sizes may be appropriate for the site, but if the flow is too large, submerged flow will occur and you won't get good measurements. If the flow is too small, the flume may not provide adequate level measurement resolution. This will result in big errors. There are tables that specify flow ranges for different size flumes to help you make a correct judgment. If the placement and construction of the Parshall flume are satisfactory, you're ready to begin assessing its operation. First, take a flow measurement. This can be done with a staff gauge. If a staff gauge isn't in place, the inspector should recommend that one be installed. If there isn't one, a yardstick or carpenter's rule will work. If you are using a staff gauge, use a yardstick to make sure it's set at 0, and then read the level in feet. Make sure these measurements are taken at the right places. Take the measurement upstream from the throat at a distance 2/3 the length of the convergence wall. This should also be where the plant's liquid level measuring device is located. You can determine the appropriate flow rate from an equation, standard curve, or a table like this one. The typical flow equation needs to be adjusted if the flow is submerged. You can often determine whether the flow is submerged by just looking at the flow pattern in the throat or divergent sections. If the jump or standing wave occurs here at the end of the divergent section where the flume enters the channel, there's free flow. But if the jump occurs here at the point where the throat enters the divergent section, the flow is submerged. If you aren't sure whether the flow is free or submerged, a simple calculation will answer the question. First, take a liquid head measurement in the convergence section, as I mentioned before. At the same time, take an additional head measurement at the point in the throat just before the flow enters the divergent section. Most treatment plants don't have measurement devices here, so just use the yardstick. To determine the percent of submergence, divide the throat head measurement in feet by the convergence head measurement in feet and multiply by 100. Generally, if the flow is running free, the ratio between the measurement in the throat section and in the convergence section is less than 50%. This may increase to 80% for throat widths 8 feet or greater. Next, visually inspect the flows upstream of the flume. The flow should be free of turbulence boils and other distortions. Approach and flow velocities at the level measurement device locations are also very important. If the velocities are too high, the accuracy of the instruments may be affected because of the turbulence. Generally, flow velocities for small flumes should not be more than 0.5 meter per second, and for large flumes, no more than 2 meters per second. The flow should be laminar and consistent across the width of the flume. Finally, check to see that both the upstream and downstream channels of the flume are free of debris and deposits. Deposits could mean the flume is sized too large or it is set incorrectly in the channel. Remember, one of the advantages of a properly operating flume is that it is self-cleaning. If there is an accumulation of debris or scaling, there's a problem.
That about covers the inspection of the primary device or Parshall flume itself. But at many plants, the flow measurement system includes secondary devices, such as ultrasonic transducers, bubblers, and floats.
These devices translate the hydraulic or liquid head measurement into the desired flow measurement. There are many different kinds of secondary devices, too many to cover in this video. The best advice is to follow the manufacturer's recommendations for evaluating each specific measuring device. But there are 4 questions you should ask as you inspect these secondary devices. Is the secondary device properly located? The secondary device should be 2/3 the distance of the convergence section wall upstream from the throat. Has the device had adequate maintenance? Make sure there's a schedule for calibration and maintenance as recommended by the manufacturer. Is the 0 setting correct? Check to see that the head measurement device is 0 to the appropriate setting. Did you read the output correctly? Human error is a common cause of inaccurate measurements. Make sure you understand the calibrations and interpret them correctly. If a stilling well is used, make sure that the stilling well is not filled with debris. Clogging causes erroneous results. Also check that the tap for the stilling well is in the proper location. Stilling wells, as you know, eliminate the effects of surface velocity or turbulent flow at the head measurement device. Here are a few tips about some of the more common secondary devices. Hook gauges are easily damaged during use, so check them carefully. Staff gauges need regular cleaning to get accurate readings at the meniscus. Float types require frequent cleaning to prevent sticking and buoyancy changes. Check for corroded hinges. Boat-type floats should be installed on the center line. Oil and grease on dipper types can foul probes. Ultrasonic types are subject to error from turbulence and foam. Wind and ice are problems for wired float types. Check all types for evidence of drift.
Now that you've examined both the primary and secondary devices, it's time to verify the whole flow management system. This can be done by comparing the flow measurements you've obtained with the readings from the wastewater treatment plant equipment.
This can be done by comparing the flow measurements you've obtained with the readings from the wastewater treatment plant equipment. Your reading should be within 10% of the plant's measurements taken at the same time. Optimally, comparison should be made at several different flow rates, but this isn't always possible. If the permit requires that the flow be recorded as the daily average flow measured by a totalizer, the inspector should also check the accuracy of the equipment calibration. If the plant exhibits fairly steady flow for periods of 10 minutes or more, this can be done rather simply. Start a stopwatch at the same time the totalizer starts to change a digit. After at least 10 minutes, read the totalizer again, just as the digits are changing. A flow rate can be calculated by subtracting the 2 totalizer readings and dividing by the measured time period. This calculated flow rate can be compared to the flow determined by an actual measurement of the head made at the primary device. If it is well within 10%, then it should be satisfactory. It's also a good idea to evaluate data, handling, reporting, and quality control of flow measurement. The wastewater treatment plant is required to maintain records of data for 3 years. Review these records and note the frequency of routine operations, maintenance inspections, flow meter calibration, and the uniformity of the flows reported. Quality control areas to evaluate include the proper operation and maintenance of equipment, accuracy of records, valid flow measurement techniques, precision of the flow data, and frequency of calibration checks.
Well, that about covers the inspection of Parshall flumes, the secondary devices, and the entire flow measurement system. Let's review the most common problems found during inspections and the basic areas that should be covered in each inspection.
Step 1 is the evaluation of the primary device, the Parshall flume. Check the location, check the materials, check the construction, check the operation, and check maintenance and calibration. Step 2 is an evaluation of the secondary device. Check the location, check maintenance, check calibration, and make sure you read the output correctly. And step 3 is the verification and certification of the system as a whole. Check that your measured flow data agrees with flows measured by the wastewater treatment plant. Check data handling and reporting, and check the permittee's quality control.
What you inspect at each plant will of course vary depending on the site-specific conditions. But I hope I've given you an understanding of the steps you might perform in an inspection. Good luck.